Hello, this is the part 3 of chapter 1.8, and we will talk about visualization of graphic transformations, how we can actually sketch metric transformations. And just to remind you that we can represent our transformation by just matrix multiplication. We have matrix A, which we multiply by vector a vector X in m-dimensional space, and it gives us a vector B in the m-dimensional space. So we often say that we transform vector X into the AX. So let's try to sketch several before and after points. For example, here we're given reasonably simple matrix A, which defines the transformation from three-dimensional space to the three-dimensional space. Let's just explicitly calculate this transformation and try to sketch 2-3 points before and after transformation, or original vectors in their image. So again, we start by writing down our vector X using 3 arbitrary components, X1, X2, and X3. And we know that we can just find the image by multiplying matrix A by vector X. So we will use the rules for multiplication of matrices and vectors. And our matrix A is very convenient because when we multiply the first row on the vector X, the only non-zero entry is the first one here. So the first component of our image will be just have X1 as an entry. Then the second row also have only one non-zero component at X2. And the third row is pretty much all zero. So no matter what kind of value of X3 we are working with, we always will have the 0 for the third component of our vector image vector. And that's a very interesting case. Although technically, our transformation going from R3 to R3, we are getting the third coordinate equals 0. So let's just try to sketch several points to see how that works. So for example, we take points here, and when we transform in it, it should have the same coordinates x1 and x2, but the third one should equal 0. So it's fall on the x3 is equal 0 plane. We can take another one and it also drops on x3 is equal 0. So basically what we're doing here is just zeroing one of the component. And this kind of operation usually refers to projections. So we are reducing the space here. We're preserving everything except for the third component, which should be equal 0. And we just say that there is now two-dimensional plane. Our solution represents a two-dimensional plane. And this is where the case which you probably was confused in the previous slide, because I told you about the range and the codomain, and I mentioned that they are not the same. And this is exactly the case here. Technically, we are going, our transformation going from R3 to R3. So technically, our codomain has 3 dimensions, but because our third component is equal 0, the resulting image will be actually a plane. And this is the case when our range, or set of all images, and our codomain, or a direct dimension of the transformation, is quite different. And the geometrically, like sketching things, really helps to understand it. Okay, so it's one interesting transformation. Let's look at the example of another transformation. For example, a shear transformation, which is very, very common in science, engineering, computer graphics. So basically here, we try to take a vector, then measure the distance between the vector and given line which going through the origin, and then we'll shift it proportionally to distance between our vector and a given line. And it's probably confusing. It's a handful of definition, but let's just see the example here. So we basically have an image of a ship on the two-dimensional plane. And each image has a bunch of points, and every single point has X and Y coordinate. And our transformation applied to this image of the ship will transform the image in something different. So let's see how that works. Let's just choose the point right here. And we will try to shear it along the X-axis, which means that we will measure the difference between that point and the X-axis, which is pretty small distance. So as soon as we measured it, we can shift our point in the direction of X-axis with a distance proportional to its distance to X1. So that will be pretty close. So we shift this point a little bit to the right. Now let's say take points here on the top of the ship's head. It's pretty far from X1. So now when we shift it to the direction of X-axis, it will be much larger distance. And we can repeat it with every single point in our ship image. And what we get is this kind of stretched the ship. It's now long and lean, and it also leans to the right. And by the way, depending on the parameters we choose, proportionality parameter we choose, we can also make this shape short and stubby. So very interesting application, and this transformation can be always represented by the matrix. On the plane, it will be a two-dimensional matrix. On the three-dimensional space, it will be three-dimensional matrix, but it's always a matrix. So for example, let's apply this matrix to our, now not the whole ship, that takes a while, but computer can do it in no time, but we will apply it to just one corner of our image, the point 0, 2, like this corner. And we will see where our corner go. I say that it should be somewhere to the right, but let's calculate precise location of our corner. So we start the definition of our transformation as a matrix A times the coordinates of a vector for our corner 0, 2. So when we perform simple matrix calculations, it gives us location of the image point for our corner is 6, 2, which is, yeah, this is pretty much where it goes. So, and we can do it for every single point and get the new image. Okay, so now I would like you to go back to the chapter 1.8 and read through a couple more examples of interesting transformations.